Welcome to the channel Next Gen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Data Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You created a new version of a Dataflow streaming data ingestion pipeline that reads from pub/sub and writes to BigQuery. The previous version of the pipeline that runs in production uses a 5-minute window for processing. You need to deploy the new version of the pipeline without losing any data, creating inconsistencies, or increasing the processing latency by more than 10 minutes. What should you do? The options are: Option A, update the old pipeline with the new pipeline code. Option B, snapshot the old pipeline, stop the old pipeline, and then start the new pipeline from the snapshot. Option C, drain the old pipeline, then start the new pipeline. Option D, cancel the old pipeline, then start the new pipeline.
To arrive at the correct answer, we focus on the keywords: Dataflow streaming, 5-minute window, without losing any data, creating inconsistencies, increasing the processing latency by more than 10 minutes.
The correct answer is option C, drain the old pipeline, then start the new pipeline.
Why is this correct? C. Draining allows the pipeline to cleanly finish processing buffered data in its 5-minute windows without data loss. Since draining takes roughly the duration of the window, it will complete well within the 10-minute latency limit before the new pipeline begins. Why are the others incorrect? A. In-place updates require strict state compatibility between the old and new pipeline code. This method is not guaranteed to work if the pipeline topology or internal state structures have changed. B. Creating a snapshot and restoring from it adds unnecessary complexity and risks compatibility issues if the new code alters the topology, whereas draining is safer and natively meets all constraints. D. Canceling the pipeline halts processing immediately. This drops buffered, in-flight data and directly violates the strict requirement to deploy without losing any data.
Your organization's data assets are stored in BigQuery, pub/sub, and a PostgreSQL instance running on Compute Engine. Because there are multiple domains and diverse teams using the data, teams in your organization are unable to discover existing data assets. You need to design a solution to improve data discoverability while keeping development and configuration efforts to a minimum. What should you do? The options are: Option A, use Data Catalog to automatically catalog BigQuery datasets. Use Data Catalog APIs to manually catalog pub/subtopics and PostgreSQL tables. Option B, use Data Catalog to automatically catalog BigQuery datasets and pub/subtopics. Use Data Catalog APIs to manually catalog PostgreSQL tables. Option C, use Data Catalog to automatically catalog BigQuery datasets and pub/subtopics. Use custom connectors to manually catalog PostgreSQL tables. Option D, use customer connectors to manually catalog BigQuery datasets, pub/subtopics, and PostgreSQL tables.
To arrive at the correct answer, we focus on the keywords: BigQuery, pub/sub, and a PostgreSQL instance running on Compute Engine, keeping development and configuration efforts to a minimum.
The correct answer is option B, use Data Catalog to automatically catalog BigQuery datasets and pub/subtopics. Use Data Catalog APIs to manually catalog PostgreSQL tables.
Why is this correct? B. Data Catalog natively supports automatic cataloging of BigQuery datasets and pub/subtopics, minimizing effort. For unsupported sources like the PostgreSQL instance on Compute Engine, Data Catalog APIs can be used to manually create custom entries. Why are the others incorrect? A. This option requires manually cataloging pub/subtopics, which is unnecessary since Data Catalog natively supports automatic cataloging for them, leading to extra development effort. C. Deploying and managing custom connectors for PostgreSQL requires more configuration and development overhead than directly using the data catalog APIs to create custom entries. D. Manually cataloging BigQuery and pub/sub assets using custom connectors ignores data catalog's native automatic cataloging capabilities, significantly violating the requirement to minimize development.
You need to create a SQL pipeline. The pipeline runs an aggregate SQL transformation on a BigQuery table every 2 hours and appends the result to another existing BigQuery table. You need to configure the pipeline to retry if errors occur. You want the pipeline to send an email notification after 3 consecutive failures. What should you do? The options are: Option A, use the BigQuery upsert table operator in Cloud Composer, set the retry parameter to 3, and set the email_on_failure parameter to true. Option B, use the BigQuery insert job operator in Cloud Composer, set the retry parameter to 3, and set the email_on_failure parameter to true. Option C, create a BigQuery scheduled query to run the SQL transformation with schedule options that repeats every 2 hours, and enable email notifications. Option D, create a BigQuery scheduled query to run the SQL transformation with schedule options that repeats every 2 hours, and enable notification to pub/sub topic. Use pub/sub and cloud functions to send an email after 3 failed executions.
To arrive at the correct answer, we focus on the keywords: SQL pipeline, aggregate SQL transformation, BigQuery table, every 2 hours, appends the result to another existing BigQuery table, retry if errors occur, send an email notification after 3 consecutive failures.
The correct answer is option D. Create a BigQuery scheduled query to run the SQL transformation with schedule options that repeats every 2 hours, and enable notification to pub/sub topic. Use pub/sub and cloud functions to send an email after 3 failed executions.
Why is this correct? D. BigQuery scheduled queries natively handle recurring SQL, appending results, and retries. Routing notifications to pub/sub allows a cloud function to track failure counts and send custom emails only after 3 consecutive failures, perfectly meeting the requirements. Why are the others incorrect? A. Cloud Composer is overly complex for a simple scheduled query. Furthermore, BigQuery upsert table operator is designed for table upsert operations, not for executing arbitrary aggregate SQL transformations. B. While BigQuery insert job operator can run SQL, deploying Cloud Composer introduces unnecessary infrastructure and operational overhead for a straightforward recurring SQL query that BigQuery natively schedules. Why are the others incorrect? C. BigQuery scheduled query native email notifications trigger on individual job failures. They lack the built-in state tracking required to send alerts only after 3 consecutive failures.
You are monitoring your organization's data lake hosted on BigQuery. The ingestion pipelines read data from pub/sub and write the data into tables on BigQuery. After a new version of the ingestion pipelines is deployed, the daily stored data increased by 50%. The volumes of data in pub/sub remained the same and only some tables had their daily partition data size doubled. You need to investigate and fix the cause of the data increase. What should you do? The options are: Option A, 1. Check for duplicate rows in the BigQuery tables that have the daily partition data size doubled. 2. Schedule daily SQL jobs to deduplicate the affected tables. 3. Share the deduplication script with the other operational teams to reuse if this occurs to other tables. Option B, 1. Check for code errors in the deployed pipelines. 2. Check for multiple writing to pipeline BigQuery sync. 3. Check for errors in cloud logging during the day of the release of the new pipelines. 4. If no errors, restore the BigQuery tables to their content before the last release by using time travel. Option C, 1. Check for duplicate rows in the BigQuery tables that have the daily partition data size doubled. 2. Check the BigQuery audit logs to find job IDs. 3. Use cloud monitoring to determine when the identified Dataflow job started and the pipeline code version. Point 4. When more than one pipeline ingests data into a table, stop all versions except the latest one. And the remaining options are: Option D, 1. Roll back the last deployment. Point 2. Restore the BigQuery tables to their content before the last release by using time travel. Point 3. Restart the Dataflow jobs and replay the messages by seeking the subscription to the timestamp of the release.
To arrive at the correct answer, we focus on the keywords. Ingestion pipelines read data from pub/sub, new version of the ingestion pipelines is deployed, volumes of data in pub/sub remain the same, only some tables had their daily partition data size doubled, investigate and fix the cause of the data increase.
The correct answer is option C, 1. Check for duplicate rows in the BigQuery tables that have the daily partition data size doubled. Point 2. Check the BigQuery audit logs to find job IDs. Point 3. Use cloud monitoring to determine when the identified Dataflow job started and the pipeline code version. Point 4. When more than one pipeline ingests data into a table, stop all versions except the latest one. Review the options on screen.
Why is this correct? C. Unchanged pub/sub volume but doubled table size implies duplicate processing, likely from concurrent pipeline versions. Checking for duplicates, identifying job IDs, checking pipeline versions, and stopping older versions methodically investigates and fixes the root cause. Why are the others incorrect? A. Scheduling daily deduplication scripts is a reactive workaround that only treats the symptom of the issue rather than identifying and permanently fixing the actual root cause in the ingestion pipelines. B. Time travel only restores past data, it does not stop the pipelines from continuing to ingest duplicate data. Also, relying solely on error logs might miss logical duplication issues without errors. Why are the others incorrect? D. Blindly rolling back and replaying messages does not properly investigate the root cause. If multiple pipeline versions were running concurrently, simply replaying messages might cause further data duplication.
You have a BigQuery dataset named customers. All tables will be tagged by using a data catalog tag template named GDPR. The template contains one mandatory field, has_sensitive_data, with a Boolean value. All employees must be able to do a simple search and find tables in the dataset that have either true or false in the has_sensitive_data field. However, only the human resources, HR, group should be able to see the data inside the tables for which has_sensitive data is true. You give the All Employees group the BigQuery.metadata viewer and BigQuery.connection user roles on the dataset. You want to minimize configuration overhead. What should you do next? The options are: Option A, create the GDPR tag template with private visibility. Assign the BigQuery.data viewer role to the HR group on the tables that contain sensitive data. Option B, create the GDPR tag template with private visibility. Assign the data catalog.tag template viewer role on this tag to the All Employees group, and assign the BigQuery.data viewer role to the HR group on the tables that contain sensitive data. Option C, create the GDPR tag template with public visibility. Assign the BigQuery.data viewer role to the HR group on the tables that contain sensitive data. Option D, create the GDPR tag template with public visibility. Assign the data catalog.tag template viewer role on this tag to the All Employees group, and assign the BigQuery.data viewer role to the HR group on the tables that contain sensitive data.
To arrive at the correct answer, we focus on the keywords. Data catalog tag template. All employees must be able to do a simple search and find tables. Only the human resources, HR, group should be able to see the data, minimize configuration overhead.
The correct answer is option C, create the GDPR tag template with public visibility. Assign the BigQuery.data viewer role to the HR group on the tables that contain sensitive data.
Why is this correct? C. Public visibility allows users with metadata view access to see tags, fulfilling the search requirement. Granting BigQuery.DataViewer to HR ensures they can see sensitive data, while minimizing configuration overhead. Why are the others incorrect? A. Private visibility requires explicit tag viewing permissions. Without them, employees cannot search the tags, failing the core requirement. B. Although assigning the tag viewer role works with private visibility, it introduces unnecessary configuration overhead compared to using public visibility. D. Public visibility already grants tag access based on underlying metadata permissions. Explicitly assigning the tag template viewer role adds unnecessary configuration overhead.
You are creating the CI/CD cycle for the code of the directed acyclic graphs, DAGs, running in Cloud Composer. Your team has two Cloud Composer instances, one instance for development and another instance for production. Your team is using a Git repository to maintain and develop the code of the DAGs. You want to deploy the DAGs automatically to Cloud Composer when a certain tag is pushed to the Git repository. What should you do? The options are: Option A, 1. Use Cloud Build to copy the code of the DAG to the cloud storage bucket of the development instance for DAG testing. Point 2. If the tests pass, use Cloud Build to copy the code to the bucket of the production instance. Option B, 1. Use Cloud Build to build a container with the code of the DAG and the Kubernetes pod operator to deploy the code to the Google Kubernetes Engine (GKE) cluster of the development instance for testing. Point 2. If the tests pass, use the Kubernetes pod operator to deploy the container to the GKE cluster of the production instance. Option C, 1. Use Cloud Build to build a container and the Kubernetes pod operator to deploy the code of the DAG to the Google Kubernetes Engine (GKE) cluster of the development instance for testing. Point 2. If the tests pass, copy the code to the cloud storage bucket of the production instance. And the remaining options are: Option D, 1. Use Cloud Build to copy the code of the DAG to the cloud storage bucket of the development instance for DAG testing. Point 2. If the tests pass, use Cloud Build to build a container with the code of the DAG and the Kubernetes pod operator to deploy the container to the Google Kubernetes Engine (GKE) cluster of the production instance.
To arrive at the correct answer, we focus on the keywords CI/CD cycle, Cloud Composer, deploy the DAGs automatically.
The correct answer is option A, 1. Use Cloud Build to copy the code of the DAG to the cloud storage bucket of the development instance for DAG testing. Point 2. If the tests pass, use Cloud Build to copy the code to the bucket of the production instance. Review the options on screen.
Why is this correct? A. Cloud Composer automatically synchronizes DAGs from its associated cloud storage bucket. Using Cloud Build to copy DAG files to the development bucket, testing, and then copying them to the production bucket is the standard CI/CD workflow. Why are the others incorrect? B. Deploying DAGs directly to the GKE cluster using Kubernetes pod operator is incorrect. Kubernetes pod operator is an airflow operator for running tasks, not a deployment mechanism. DAGs must be copied to the associated cloud storage bucket. C. Using Kubernetes pod operator to deploy DAGs directly to GKE is incorrect. Cloud Composer expects DAG Python files to be placed in the specific cloud storage bucket created for the environment. D. Deploying to the production environment's GKE cluster using Kubernetes pod operator is incorrect. Cloud Composer requires DAG files to be copied to the production environment's cloud storage bucket for deployment.
You have a BigQuery table that ingests data directly from a pub/sub subscription. The ingested data is encrypted with a Google-managed encryption key. You need to meet a new organization policy that requires you to use keys from a centralized cloud key management service, Cloud KMS, project to encrypt data at rest. What should you do? The options are: Option A, use Cloud KMS encryption key with Dataflow to ingest the existing pub/sub subscription to the existing BigQuery table. Option B, create a new BigQuery table by using Customer Managed Encryption Keys, CMEK, and migrate the data from the old BigQuery table. Option C. Create a new pub/subtopic with CMEK and use the existing BigQuery table by using Google Managed Encryption Key. Option D. Create a new BigQuery table and pub/subtopic by using Customer Managed Encryption Keys, CMEK, and migrate the data from the old BigQuery table.
To arrive at the correct answer, we focus on the keywords BigQuery table, Google Managed Encryption Key, Cloud Key Management Service, Cloud KMS, encrypt data at rest.
The correct answer is option B. Create a new BigQuery table by using Customer Managed Encryption Keys, CMEK, and migrate the data from the old BigQuery table.
Why is this correct? D. BigQuery encryption keys cannot be changed after table creation. You must create a new table with CMEK and migrate existing data to meet the requirement for encrypting data at rest. Why are the others incorrect? A. The existing BigQuery table still uses Google Managed Keys. Adding Dataflow does not change the encryption of the existing table at rest. C. Changing the pub/subtopic encryption does not encrypt the data at rest in the existing BigQuery table. The table still uses Google Managed Keys. D. The requirement is only to encrypt data at rest. Creating a new pub/subtopic is unnecessary and disruptive to the existing ingestion pipeline.
You created an analytics environment on Google Cloud so that your data scientist team can explore data without impacting the on-premises Apache Hadoop solution. The data in the on-premises Hadoop Distributed File System, HDFS, cluster is in optimized row columnar, ORC, formatted files with multiple columns of Hive partitioning. The data scientist team needs to be able to explore the data in a similar way as they used the on-premises HDFS cluster with SQL on the Hive query engine. You need to choose the most cost-effective storage and processing solution. What should you do? The options are: Option A, import the ORC files to Bigtable tables for the data scientist team. Option B, import the ORC files to BigQuery tables for the data scientist team. Option C, copy the ORC files on cloud storage, then deploy a Dataproc cluster for the data scientist team. Option D, copy the ORC files on cloud storage, then create external BigQuery tables for the data scientist team.
To arrive at the correct answer, we focus on the keywords optimized row columnar, ORC, formatted files, multiple columns of Hive partitioning, SQL on the Hive query engine, most cost-effective storage and processing solution.
The correct answer is option D. Copy the ORC files on cloud storage, then create external BigQuery tables for the data scientist team.
Why is this correct? D. BigQuery external tables directly query ORC files on cloud storage and natively support Hive partitioning. This serverless approach avoids data duplication and persistent compute costs, making it the most cost-effective solution for SQL exploration. Why are the others incorrect? A. Cloud Bigtable is a NoSQL wide column store optimized for low-latency operational workloads. It does not natively support SQL and is entirely unsuitable for ad hoc analytical exploration of ORC files. B. Importing data into BigQuery's native storage incurs ingestion time and additional storage costs. It is less cost-effective than querying the data in place on cloud storage using external tables. C. While Dataproc provides a familiar Hadoop environment, running a dedicated compute cluster incurs continuous infrastructure costs, making it far less cost-effective than using BigQuery's serverless external tables.
You are designing a Dataflow pipeline for a batch processing job. You want to mitigate multiple zonal failures at job submission time. What should you do? The options are: Option A, submit duplicate pipelines in 2 different zones by using the zone flag. Option B, set the pipeline staging location as a regional cloud storage bucket. Option C, specify a worker region by using the region flag. Option D, create an event arc trigger to resubmit the job in case of zonal failure when submitting the job.
To arrive at the correct answer, we focus on the keywords, Dataflow pipeline, mitigate multiple zonal failures at job submission time.
The correct answer is option C, specify a worker region by using the region flag.
Why is this correct? C. Using the region flag specifies a worker region rather than a specific zone. Dataflow will automatically select an available zone within that region, providing resilience against zonal failures at job submission time. Why are the others incorrect? A. Submitting duplicate pipelines is inefficient, doubles costs, and requires manual management instead of relying on Dataflow's built-in regional placement capabilities. B. A regional staging bucket ensures high availability for staging files but does not influence the compute worker placement or mitigate zonal failures during job submission. D. EventArc is designed for event-driven architectures and is an overly complex, non-standard approach for handling Dataflow job submission retries across zones.
You are designing a real-time system for a ride-hailing app that identifies areas with high demand for rides to effectively reroute available drivers to meet the demand. The system ingests data from multiple sources to pub/sub, processes the data, and stores the results for visualization and analysis in real-time dashboards. The data sources include driver location updates every 5 seconds and app-based booking events from riders. The data processing involves real-time aggregation of supply and demand data for the last 30 seconds, every 2 seconds, and storing the results in a low-latency system for visualization. What should you do? The options are: Option A, group the data by using a tumbling window in a Dataflow pipeline, and write the aggregated data to memory store. Option B, group the data by using a hopping window in a Dataflow pipeline, and write the aggregated data to memory store. Option C, group the data by using a session window in a Dataflow pipeline, and write the aggregated data to BigQuery. Option D, group the data by using a hopping window in a Dataflow pipeline, and write the aggregated data to BigQuery.
To arrive at the correct answer, we focus on the keywords, last 30 seconds, every 2 seconds, low latency system for visualization.
The correct answer is option B, group the data by using a hopping window in a Dataflow pipeline, and write the aggregated data to memory store.
Why is this correct? B. A hopping window accurately captures overlapping time intervals, 30 seconds of data evaluated every 2 seconds. Memory store provides the necessary ultra-low latency for serving real-time dashboard visualization lookups. Why are the others incorrect? A. Tumbling windows represent contiguous, non-overlapping time intervals, which fails to meet the requirement to aggregate the last 30 seconds of data every 2 seconds. C. Session windows group data by activity gaps, not fixed overlapping intervals. Additionally, BigQuery is a data warehouse and cannot match the ultra-low latency of memory store for rapid, continuous dashboard updates. D. Although a hopping window correctly handles the overlapping interval requirement, BigQuery is suboptimal compared to memory store for serving ultra-low latency reads to real-time visualization dashboards.
Your car factory is pushing machine measurements as messages into a pub/subtopic in your Google Cloud project. A Dataflow streaming job that you wrote with the Apache Beam SDK reads these messages, sends acknowledgement to pub/sub, applies some custom business logic in a doFn instance, and writes the result to BigQuery. You want to ensure that if your business logic fails on a message, the message will be sent to a pub/subtopic that you want to monitor for alerting purposes. What should you do? The options are: Option A, enable retaining of acknowledged messages in your pub/sub pull subscription. Use cloud monitoring to monitor the subscription/number_retained_act_messages metric on this subscription. Option B, use an exception handling block in your Dataflow's doFn code to push the messages that failed to be transformed through a side output and to a new pub/subtopic. Use cloud monitoring to monitor the topic/number_enact_messages_by_region metric on this new topic. Option C, enable dead lettering in your pub/sub pull subscription, and specify a new pub/subtopic as the dead letter topic. Use cloud monitoring to monitor the subscription/dead_letter_message_count metric on your poll subscription. Option D. Create a snapshot of your pub/sub poll subscription. Use cloud monitoring to monitor the snapshot/number_messages metric on this snapshot.
To arrive at the correct answer, we focus on the keywords. Dataflow streaming job reads these messages, sends acknowledgement to pub/sub, business logic fails on a message will be sent to a pub/sub topic.
The correct answer is option B. Use an exception handling block in your Dataflow's doFN code to push the messages that failed to be transformed through a site output and to a new pub/sub topic. Use cloud monitoring to monitor the topic/number_enact_messages_by_region metric on this new topic.
Why is this correct? B. In Apache Beam, site outputs are the standard way to route elements that fail processing to a dead letter queue, like a new topic, allowing the main pipeline to continue seamlessly. Why are the others incorrect? A. Retaining acknowledged messages simply stores them in the current subscription, it does not route failed messages to a separate monitoring topic. C. Pub/sub dead letter topics only catch unacknowledged messages. Since Dataflow acknowledges the message upon reading, business logic failures later in the doFN won't be caught. D. Creating a snapshot only captures the subscription state at a point in time, it cannot continuously route failed messages to a new topic.
You want to store your team's shared tables in a single dataset to make data easily accessible to various analysts. You want to make this data readable but unmodifiable by analysts. At the same time, you want to provide the analysts with individual workspaces in the same project, where they can create and store tables for their own use, without the tables being accessible by other analysts. What should you do? The options are: Option A. Give analysts the BigQuery data viewer role at the project level. Create one other dataset, and give the analysts the BigQuery data editor role on that dataset. Option B. Give analysts the BigQuery data viewer role at the project level. Create a dataset for each analyst, and give each analyst the BigQuery data editor role at the project level. Option C. Give analysts the BigQuery data viewer role on the shared dataset. Create a dataset for each analyst, and give each analyst the BigQuery data editor role at the dataset level for their assigned dataset. Option D. Give analysts the BigQuery data viewer role on the shared dataset. Create one other dataset and give the analysts the BigQuery data editor role on that dataset.
To arrive at the correct answer, we focus on the keywords, shared tables in a single dataset, readable but unmodifiable, individual workspaces, without the tables being accessible by other analysts.
The correct answer is option C. Give analysts the BigQuery data viewer role on the shared dataset. Create a dataset for each analyst, and give each analyst the BigQuery data editor role at the dataset level for their assigned dataset.
Why is this correct? C. Assigning BigQuery data viewer on the shared dataset makes data readable but unmodifiable. Creating individual datasets and assigning BigQuery data editor on those specific datasets provides isolated workspaces. Why are the others incorrect? A. Assigning data viewer at the project level gives read access to all datasets. Giving data editor on a single other dataset does not provide individual, isolated workspaces. B. Assigning data viewer and data editor at the project level grants read and edit access to all datasets, violating the requirement for isolated workspaces and least privilege. D. Creating one other dataset for all analysts fails to provide individual workspaces, as everyone would have access to the same shared editing workspace.
You are running a streaming pipeline with Dataflow and are using hopping windows to group the data as the data arrives. You noticed that some data is arriving late but is not being marked as late data, which is resulting in inaccurate aggregations downstream. You need to find a solution that allows you to capture the late data in the appropriate window. What should you do? The options are: Option A. Use watermarks to define the expected data arrival window. Allow late data as it arrives. Option B. Change your windowing function to tumbling windows to avoid overlapping window periods. Option C. Change your windowing function to session windows to define your windows based on certain activity. Option D. Expand your hopping window so that the late data has more time to arrive within the grouping.
To arrive at the correct answer, we focus on the keywords, streaming pipeline with Dataflow, some data is arriving late but is not being marked as late data, capture the late data in the appropriate window.
The correct answer is option A, use watermarks to define the expected data arrival window. Allow late data as it arrives.
Why is this correct? A. Watermarks define when Dataflow expects all data for a window to have arrived. Allowing late data based on watermarks ensures late arriving records are correctly captured and processed in their appropriate event time windows. Why are the others incorrect? B. Tumbling windows are fixed, non-overlapping windows. Changing the window type alters the grouping logic but does not provide a mechanism to track or handle late arriving data based on event time. C. Session windows group data by activity bursts. Altering the windowing strategy to session windows does not resolve the underlying issue of how the system handles late arriving data. D. Expanding the window size increases the window duration but does not instruct Dataflow on how to track expected arrival times or correctly handle late data, potentially increasing latency.
You work for a large e-commerce company. You store your customers' order data in Bigtable. You have a garbage collection policy set to delete the data after 30 days, and the number of versions is set to 1. When the data analysts run a query to report total customer spending, the analysts sometimes see customer data that is older than 30 days. You need to ensure that the analysts do not see customer data older than 30 days while minimizing cost and overhead. What should you do? The options are: Option A. Set the expiring values of the column families to 29 days and keep the number of versions to 1. Option B. Use a timestamp range filter in the query to fetch the customer's data for a specific range. Option C. Schedule a job daily to scan the data in the table and delete data older than 30 days. Option D. Set the expiring values of the column families to 30 days and set the number of versions to 2.
To arrive at the correct answer, we focus on the keywords, Bigtable, garbage collection policy. Analysts sometimes see customer data that is older than 30 days. Ensure that the analysts do not see customer data older than 30 days, minimizing cost and overhead.
The correct answer is option B, use a timestamp range filter in the query to fetch the customer's data for a specific range.
Why is this correct? B. Bigtable's garbage collection runs asynchronously in the background. To guarantee queries do not return expired data before physical deletion, applications must use timestamp range filters on read requests. This ensures correctness while minimizing cost and overhead. Why are the others incorrect? A. Setting expiration to 29 days does not solve the root cause, as garbage collection remains an asynchronous background process that may still allow expired data to be queried temporarily. C. Scanning the entire table daily to manually delete data is highly inefficient, significantly increases compute costs, and creates unnecessary overhead compared to built-in features. D. Changing the number of versions to 2 does not address the asynchronous nature of garbage collection and may increase storage costs, failing to meet the requirements.
You are using a Dataflow streaming job to read messages from a message bus that does not support exactly once delivery. Your job then applies some transformations and loads the result into BigQuery. You want to ensure that your data is being streamed into BigQuery with exactly once delivery semantics. You expect your ingestion throughput into BigQuery to be about 1.5 gigabytes per second. What should you do? The options are: Option A. Use the BigQuery Storage Write API and ensure that your target BigQuery table is regional. Option B. Use the BigQuery Storage Write API and ensure that your target BigQuery table is multi-regional. Option C. Use the BigQuery Streaming API and ensure that your target BigQuery table is regional. Option D. Use the BigQuery streaming API and ensure that your target BigQuery table is multi-regional.
To arrive at the correct answer, we focus on the keywords, exactly once delivery semantics, 1.5 gigabytes per second.
The correct answer is option B. Use the BigQuery Storage Write API and ensure that your target BigQuery table is multi-regional.
Why is this correct? B. The Storage Write API natively supports exactly once delivery. Multi-regional tables provide a default quota of 3 gigabytes per second, which easily accommodates the expected 1.5 gigabytes per second throughput. Why are the others incorrect? A. The default storage write API quota for regional locations is only 300 megabytes per second, which cannot support the required 1.5 gigabytes per second throughput without a quota increase. C. The legacy streaming API lacks native exactly once semantics, and regional locations have quotas too low for 1.5 gigabytes per second throughput. D. While multi-regional tables offer higher quotas, the legacy streaming API lacks the robust native exactly once delivery support provided by the Storage Write API.